And now what we want to look at is a reheat regenerative cycle. This is figure 1520 in the book, so you may want to open that up. I copied it here, so we have that. And now what we're going to do is I'll put numbers associated with this, and we'll go through and find the enthalpies, the entropies, and all that stuff, and go through and do an example associated with this. If we look here, so we have steam coming in at state 2, expanding through the turbine to state 3. Y1 is removed, so Y1 goes over, is condensed. 1 minus Y1, so now we have 1 minus Y1 is reheated. So it goes back, 1 minus Y1 goes back and is reheated, comes back into turbine 2. It expands partway through the turbine and Y2 is removed. It condenses and 1 minus Y1 minus Y2 expands and leaves the turbine. And here we have this same thing going on. So we see that here, we have Y2 here. And so we have the expansion through the turbine back, expand to the turbine, expand through the turbine, different fractions about the two pumps, etc. And so now, let's, for the following, we'll let P2 equal 10 MPa. P2 is 500 degrees C. P3 is equal to 1500 kPa. P4 is 1500 kPa. T4 is 500 degrees C. Now actually, there'd be a pressure drop, so there are pressure drops everywhere, so P4 wouldn't be the same. There'd be a pressure drop to go through the reheater and back here. And typically the temperatures are not the same, but our steam tables don't have 450, so for our purposes it's easier just to look it up. We're going to have that P5 is equal to 250 kPa, and that P6 is equal to 10 kPa. So anyway, these are the numbers, and then we go through and look up the enthalpies as we've done before. We've used these numbers before, so we've looked them up, so it makes life slightly easier. Not too much easier, but slightly easier. So H2 is equal to 3376.5. S2 is 6.5982. H3 is equal to 2868.1. So that's at P3, so we have an isentropic expansion. H4 is equal to 3472.5. S4 is equal to 7.5664. So now, we were here, it went through the reheater, the entropy is greater, so notice that S4 is greater than S2, we have that going on, so we can't use these same values, so I now have to use this entropy value to find the others. So I have that P5 is equal to 250 kPa, S5 is equal to S4, we have that H5 is equal to 2950.9. And I have that P6 is equal to 10 kPa, S6 is equal to S4, and so I have that H6 is equal to 2398.7. Now, you're going to have to calculate the quality to find this, so you'll have to do that. And, oh, speaking of which, I wrote it down. So X here, X was equal to 92.2%. So normally in turbines, they're designed, this is an aside, they're designed so the quality exiting the turbine is about 95%. You don't want it too much lower or you get impingement, but the water condenses and you get liquid droplets whacking the blades and eroding them. So I have, where am I, H6, not distracting myself. H7 is equal to 191.8. H8 is equal to 191.8 plus V delta P 0.001 times 250 minus 10. So that's equal to 192. H9 is equal to H sub F at 250 kPa is equal to 535.2. H10 is equal to H9 plus V delta P. So that's equal to 535.2 plus 0.001 times 10,000 minus 250. So H10 is equal to 545. Now going back and erasing some things. H1 is equal to HA is equal to H sub F at 1500 kPa. So H1 is equal to 844.5. And with that, we have found all the enthalpies around the cycle. And now we have that. So the next thing is we're going to find Y1 and Y2. And then we'll do the first law analysis on the turbine, the pump, the heat in, etc. So we'll find Y1 with the first law. So with Y1 at H3, we have everything leaves at H1. We have Y1 at HA, and we have everything coming in at H10. And so if I look at this, we have Y1 H3 plus H10 is equal to H1 plus Y1 HA. And so I have Y1 is equal to H1 minus H10 over H3 minus HA is equal to 844.5 minus 545 over 2868.1 minus 844.5. So we have Y1 is equal to 0.148, and 1 minus Y1 is equal to 0.852. So when I find Y1, very often I'll find 1 minus Y1 because I know I'm going to need that term for the turbine expansion. Here, I'm going to need 1 minus Y1, so, and I'll probably need that when I do the first law on the second heat exchanger. So I often find the numbers so it makes life easier. And now I'll do the second heat exchanger. So you have this information, and now let's do it for the second heat exchanger. So I have Y2 H5. I have everything leaving at H7. I have Y1 at HA. And I have 1 minus Y1 minus Y2 coming in at H8. So here's the energy diagram for the second heat exchanger. So if we do the first law, we have Y2 H5 plus Y1 HA plus 1 minus Y1 minus Y2 H8 is equal to 100% at H9. So if I solve for this, I have Y2 times H5 minus H8 plus Y1 times HA minus H8 is equal to H9 minus H8. So in this case, I know all the enthalpies and I know Y1, and if I substitute all that stuff in, I solve for Y2, and Y2 is equal to 0.089. And 1 minus Y1 minus Y2 is equal to 0.763. So I know I'm going to need these numbers as well. So this is the first law. I have 3 things coming in and 1 thing leaving. I solve for this, substitute in, it's about 3 lines of numbers, and then I get Y2 is equal to this. So at this point, we found all the enthalpies and the mass fractions, and now we can do our first law on the turbine, the pump, the heat in, etc. So if I look at the turbine, I have everything going between 2 and 3. So WT is equal to 1 times H2 minus H3 plus 1 minus Y1 between H4 and H5. So between 4 and 5, I have 1 minus Y1. And then between 5 and 6, I have minus Y1 minus Y2 as we subtract that up. Plus 1 minus Y1 minus Y2, H5 minus H6. So if I substitute all these numbers in, I have the result for this term is 508.4. The result for this term is 444.4. And the result for this term is 420.6. So it's fairly evenly divided. And so I have that WT is equal to 1373.4 kilojoules per kilogram. WP1 is equal to 1 minus Y1 minus Y2 times H8 minus H7. So that's equal to 0.15. Then we find the second pump work, WP2, is equal to 1 times H10 minus H9. And so that's equal to 9.8. And WP total, we add that together, we get 10.0. So 9.95 will be 10.0. Then we can solve for the net work. So before I erase this, so we have the work of the turbine, the work of the pumps, subtract them, find the net work. So W net is WT minus WP is equal to 1363.4. And then we can find Q in, so we'll look for Q in. And Q in is in 2 parts. So I have heating. So I have heating from 1 to 2. and I have heating from 3 to 4. So all of it is heated between H2 minus H1, and we extracted Y1, so 1 minus Y1 is heated between H4 and H3. So if I substitute in and do this, this is 2532 when I subtract this, and this is 514.9. So we see most of the heat comes from 1 to 2, and then but we add some more heat, and this heat is added at a higher temperature, so we're raising the average temperature of heat addition, which we know improves cycle efficiency. So Qn is equal to 3046.9. The thermal efficiency, W net over Qn, is equal to 1363.4 over 3046.9 is equal to 0.447. So I have that. And I'm going to find the mass flow rate. So now we'll give, let's say we want the network to be 500 megawatts as we've talked before. Then we'll find the mass flow rate. We'll just do a slightly different calculation and find pipe diameters. So if W naught net is equal to 500 megawatts, then I can find the mass flow rate of the steam times W dot net is equal to 500,000. So N dot S is 500,000 divided by 1363.4 is equal to 366.73 kilograms per second. And now what I wanted to do is, what is the diameter of the pipe? So if I looked at, what is the diameter of this pipe? I'm curious about that. It's like, how big should the pipe be? And so what I did is I looked up what the recommended velocity of steam, superheated steam through a pipe is. And so what happened is we're given that the velocity V is about 50 meters per second. And I could look up V2, the specific volume 2 is 0.032747 cubic meters per kilogram. And the mass flow rate is equal to the area times the velocity divided by the specific volume. So we have 366.7 is equal to A times 50, the velocity divided by the specific volume, 0.032747, good grief. And so then I can find that the area is 0.2402 square meters. A is equal to pi over 4d squared. So D is equal to 0.55 meters, or 55 centimeters. And so that tells us what it is. So we have a pipe like that. But you need to know the velocity to do this. But this is an extension, just like we found the mass flow rate and things like that. You can look for the area. So if I knew, for the condenser, if I knew what the velocity was, let's say 100 meters per second, 150 meters per second, then I could find out what is that area. And you find out it's really big. And so those are all types of things that can be determined. But it comes from doing the analysis on the power plant that we're doing, and all these other things are extensions. So you have experience doing some of this. For homework, do 1542 And here, use 10 MPa, 550 degrees C, and 2.5 MPa. So this is so you can look things up in the steam tables. And 1543, and here we're changing the pressures as well. 5 MPa, not 4.9 and 4.6 MPa. So in the problem statement, they're looking at a pressure drop, so we're not going to deal with that. Use 500 kPa instead of not 760 kPa and 7.5 kPa. So you'll do that.